Hi everyone. Sorry again about bad Wi-Fi today. I hope this is a reasonable alternative. To pick up where we left off, we were talking about a linear first-order differential equation, which some people might not have seen before. So we have x dy dx is equal to x squared plus 3y. And we thought that you weren't able to separate them out in any way to get all the y's on one side, all the x's on the other. So in particular, what we need to do is get dy dx by itself and all the y terms on the left. So this gives us dy dx minus 3 over xy is equal to x. So again, divided everything by x and then subtracted that 3y to the other side. And then we're going to do the integrating factor. And this is just kind of glossed over in the notes, but I think it's important to see what it actually does for us. The integrating factor is you take what's out in front of your y term, including the sign, and you stick it in e to the integral of that thing. Okay, so in our particular case, we have e to the integral of minus 3 over x dx. We get that to be e to the negative 3 natural log of x. We can simplify this a little bit, right? But in order to take e to the natural log of something, the natural log and the e have to be right flush up against each other. So you have to get the negative 3 out front of the natural log to go away. We do that by bringing it inside. So I have natural log of x to the minus 3, which is 1 over x cubed. Okay, so this is what's called our integrating factor. It's going to help us out a lot. What do we do with it? We multiply each term in our differential equation by my integrating factor. And we're going to pay close attention to what happens on the left-hand side. But I get 1 over x cubed dy dx minus 3 over x to the fourth, right, times y. And you can't forget to do it on this side as well. And this is our new differential equation. All we're doing is multiplying it by a constant function, so we're allowed to do that. And what's really important to note here is that I have a function, 1 over x cubed. And if I take the derivative of that function, I get minus 3 over x to the fourth, right? It's just a power rule. At the same time, I have another function, y. Take the derivative of that, and I get dy dx. And the way they're positioned and multiplied by each other is actually a product rule. So this is actually d by dx of my function y and my function 1 over x cubed. Okay, so this is, what integrating factor does for us. It allows us to write the left-hand side as a product rule. And then when we do that, we can just integrate, right? So I integrate the left-hand side, and I just, by fundamental theorem of calculus, get y times 1 over x cubed, integrate the left-hand side, and I get minus 1 over x plus c. I forgot to give an initial condition, but we can put one in now. Initial condition is that y of 1 is equal to 0. And because we have a bunch of stuff over x, we're going to make x positive. So x can never be 0. So at this point, you can plug in your initial condition. You say that when I plug in 1 for x, I get 0 for y. So I get 0 is equal to minus 1 plus c. That tells me that c is equal to 1. And so my equation becomes y is equal to minus x squared plus cx cubed. And c was 1, so this is just plus x cubed. And this is my final equation here. It's pinpointed at one exact point, and we're good to go. Okay, so I hope this was a good example for linear differential equations. I'll write it out. Linear first order DPQs. And we saw a separable one earlier in class. Okay, so that is kind of a review of differential equations I wanted to cover today. Now we can move on to how we formulate stuff in linear algebra terms. So we learned a bit about a differential operator. we take this d by dx or d by dt, whatever you want, operator, and we give it a name. We call it d. It's a linear operator, right? We know that because d by dx of two different functions, x plus x squared, for instance. How do you do that? Well, you do d by dx of just x first, and then you add that to d by dx of x squared. Okay, so that's linear. So it's, it works with addition, it works with scalar multiplication as well, right? I can pull a scalar out and then take my derivative. So we know it's linear. And so this d by dx of a function of x literally just becomes df. And then when you raise d to some power, it's the equivalent of taking higher derivatives. So two derivatives of f of x is equal to just d squared on f, and so forth. The idea here is that once we formulate it in terms of this and this, we can start making operators out of chains of these. So I can say L is a linear combination of coefficients and the differential operator d to different powers. Okay, and we're going to use L as a way of representing our differential equations in just a simpler linear algebra way. So if we start off with an example, we can find L if y triple prime plus 2y double prime minus 4y is equal to 0. Well, essentially, y triple prime is equivalent to d cubed on y. And I have plus 2 times d squared on y. I have minus 4, but since we're working in terms of operators now, I have to put in an identity operator on y. That gives me 0. And then I can pull y out front, right? So it's linear. So I can do d cubed plus 2d squared minus 4 times the identity on y is equal to 0. And this right here is what we call L. Okay, so it operates on my function, so I can pull it all the way out to the front, and it's linear, so everything works out well. Great. There's some other stuff about L in the notes. One I want to highlight is that if L is order n, so we call it an nth order linear operator, then the highest power of d in L is n. Okay, so this is no different than an nth order polynomial. If we have a fifth order polynomial, we know the highest power can be 5, right? And the other more important one is that an nth order differential equation has exactly n solutions to it. And what we're interested in linear algebra is stuff that's linearly independent, right? So what we can do is we can check to see if they're linearly independent using the Wronskian. I know it's a bit weird to think about functions being linearly independent, but we talked a little bit about polynomials being linearly independent, right? We essentially put them in a vector, and we make sure that their coefficients don't make them linearly dependent, right? We define the Wronskian of a bunch of functions, f1, f2, up through fn. It's a square matrix, and we, in fact, take the determinant of it. We put all of our functions up along the top, and then we start taking derivatives and put them below. And you keep doing that until you run out of room. And you're going to run out of room when you get to your nth minus 1 derivative all the way. Okay, there are some confusing conditions whether or not your functions will be linearly independent based on what you get with your Wronskian, but they're pretty well outlined in the notes, so I won't cover them here in the interest of time. But essentially, you'll be using the Wronskian to determine if your solutions to your differential equation are linear, sorry, not linear, linearly independent. What we can also do are some cool tricks to figure out if an equation will give you another solution. Sorry, we'll use the Wronskian to do a cool trick where we can find another solution to a differential equation if we're given one to start with. So we have special types of differential equations. So these are second order linear differential equations. I'll call them just differential equations. The ones we look at this week look like this. So I have f double prime of x, you can use x or t, plus a function p of x out front of my f prime, and then a different function q of x sitting out front, just my normal x. And for now, we're setting this equal to 0. Okay, this is not an easy one to solve, right? There's a whole bunch of different examples all over the internet, all over textbooks that help you solve these. But to do so, you need to have one solution first. So essentially, we have this really fancy equation that says two solutions to this very special above differential equation. They satisfy a special equation that is the Wronskian, the derivative of it, over the Wronskian itself is minus p of x. Okay, so I'm going to have two solutions because it's second order. I can compile them into a Wronskian, and this relationship will hold given this p of x out front. Okay, so we're essentially creating a new equation for me to use, and now I have two equations and two unknowns, right? So it's very linear algebra-esque here that we're essentially manufacturing this equation over here to help us out. And so if you have one solution, you can use it to form a second solution. And we'll do an example to show exactly how you do that, but you use the integrating factor essentially, and you use this equation up here. So the example is find another solution to x times y double prime plus 1 plus 2x. Sorry, this is a minus. 1 minus 2x y prime plus x minus 1 y is equal to 0. Given one solution is y1 is equal to e to the x. Okay. We're not going to impose an initial condition here, but we'll say that x is greater than 0, so we don't run into any trouble with dividing by x. So our first step here is we need to get it in the form of the special differential equation we have up here. So I need to get f double prime by itself. So I have y double prime plus 1 minus 2x over x y prime plus x minus 1 over x times y is equal to 0. And then I use the Wronskian equation up here to figure out the relationship between my Wronskian and my function p. So I have that w prime of x over w of x is equal to minus 1 minus 2x over x, which is equal to 2 minus 1 over x. Okay, I can differentiate both sides. I know it's weird to think about, but I can, and I get the natural log of w, my Wronskian, is equal to 2x minus the natural log of x. Okay, and then I can solve for w. I exponentiate both sides, and I get w is equal to e to the 2x minus log of x. I know with subtraction that I can combine these into e to the 2x times e to the minus log of x. And we saw that this can simplify to 1 over x e to the 2x. Great. What do I do with that? Well, I know that's my Wronskian, right? So I know that my Wronskian will have to equal this for both of my solutions. So I'm going to define an arbitrary solution y2, and I'm going to stick it into Wronskian to find a relationship. So my Wronskian then is going to be y1, y1 prime, y2, y2 prime. I'm solving for y2, but I know what y1 is, right? I have e to the x here. I can differentiate e to the x to get e to the x by itself. I have y2 and y2 prime. And that, by definition, has to equal 1 over x e to the 2x, right? We just proved that one line above. So if I actually do that determinant on the left-hand side, I get e to the x times y2 prime minus y2. That's equal to 1 over x e to the 2x. And in particular, I have y2 prime minus y2 is 1 over x e to the x. Okay, and again, all I'm doing here is solving for y2. And what we have here is we actually have a first order linear differential equation, right? So I can scroll up a little bit here to show you, but I have a derivative. I have a function. Sorry, I have a function here. I have y, I have its derivative, and then I have another function just of x. So I have a linear first order differential equation that I've, kind of made out of what I was given. And I can solve it the same way I'm used to. So I can use the integrating factor. We know that to be e to the integral of whatever is in front of my equation itself, which is just minus 1 dx. And so I get that this is just equal to e to the minus x. Great, I multiply everything through by that, right? So I have e to the minus x times y2 prime minus e to the minus x times y2 is equal to 1 over x, and then the e's will cancel, right? So I have e to the x times e to the minus x. What this will give me here then, I look at the left-hand side pretty closely, and I'm always going to get a product rule, but it's always helpful to make sure. But I have a function here, y2, and I have its derivative here. I have another function here, e to the minus x, and I have its derivative minus e to the minus x. So this is indeed just the product of e to the minus x and y2 when you differentiate it. This is 1 over x. Again, I can integrate e to the minus x times y2 is log of x plus c. And let me go ahead and solve for y2. I get this is e to the x log of x plus c e to the x. Okay, so this is, by definition, a second equation here. And we're going to figure out what to do with that c. In particular, it doesn't matter. And this is where it starts to get a little weird. But my general solution to that differential equation, I can go ahead and take any linear combination of y1 and y2, and it will still work, right? So this right here is a solution, and so is, where to go? This right here. If I take both of them and I add them together, I send them through, this one will give me 0, right, because it's a solution. This one as well will give me 0 because it's a solution. So I can add them up together. I can take scalar multiples of them, and they will all give me, 0 plus 0 is equal to 0. Okay, so then my general solution is going to be y of x is equal to some constant a1 times y1 plus some constant a2 times y2. So if I write this out, I get a1 e to the x plus a2 e to the x log of x plus a2c e to the x. But notice that a2 and c are both arbitrary, as is a1, and it's the same function. It's e to the x in both of them. There's no point in having two separate terms with arbitrary coefficients out front. We might as well loop this with a1 into a singular constant, and we can just recall it a1. This is actually equal to a1 e to the x plus a2 e to the x log of x. Okay, and that's my equation. Note, this question only asks you to find y2, right? So you could stop there, but I wanted to show you what happens. The only caveat is if you are given an initial condition, then you have to find C, and it won't so easily decompose into something that you can combine the coefficients. Okay, great. So this is just the differential equation video. Because they're too big to send via email, I think I'm going to record a separate video on spectral decomposition. So I'm going to go ahead and do that now.